Hi everyone, in this lecture we're going to discuss another examples related to frames and machines. And in here we have a structures that is pin connected at joint A and joint C, okay? And then the structures, the frames AB over here is attached to the frame CBD using a pin connectors at B, okay? And then at the end of the frame CBD, there's a pulley with a diameter of 0.3 meter, and then the pulley is attached to the frame at D using a pin connectors as well, and then a continuous cable is running through the pulley, right? The one that I draw in red color in here is a continuous cable. At one end of the cable it is attached to a weight W, and then at the other end of the cable it is pin connected at E, okay? So in these problems we need to find the pin the reaction forces at C, and then the pin connection forces at B, okay? Knowing that the weight over here is 75 kilograms times G. Okay, G is a gravitational constant. Since we are working on the SI system, it's 9.81, so we have 735.5 Newton. Okay, and in these problems you will see the usage of a two-force member concept that we have discussed in previous lectures, okay? Because if you can observe that member AB right here, right? This member AB, it is pin connected at A and B, and there's no load applied somewhere within the members, okay? So it is a type of two-force member, and we will see later how we can utilize the concept that we have learned. So similar to other problems that we have solved, it's always a good thing to start with sketching the free body diagrams. In here we have AX, and then we have AY, okay? Here we have CX, and then we have CY, okay? And then in here we have EX, and then we have EY, and later you will show that EY is basically 0, okay? And then afterwards we can do the analysis, okay, by first making a cut, right? And the question is where we have to make a cut. And remember to the lecture that we have discussed previously that a good place where to make a cut is at the locations where the pin connectors is located. In this case, it is a good thing to make a cut at the joint B. And when I say make a cut, basically we try to detach the frame AB from the frame CBD right here, okay? Then let's draw. Okay, this is C, B, D, this is A, B, okay? So at A we have AX and AY, right? And since we make a cut at B, then we have to include the pin connector forces BY and BX, okay? Then we will have also here is BY and BX, okay? And then over here we have CX and CY, okay? And remember we still have the pulley right at D, right? And then we have this cable W with a weight W, right? And then this cable is attached to other end where it is pin supported with EX and EY, okay? Such that this free body diagrams, we can call it the upper free body diagrams, and the free body diagrams down here we can call it the lower free body diagrams, okay? Some of you may think that this upper free body diagram is still a little bit complicated, and that could be true at some point. So that why don't we try to make another cut right here? And when in here we are trying to isolate this joint right here. Okay, so I'm going to take away that joint from the upper free body diagrams. Okay, so I'm going to draw another things in here. I will have my cable right here at joint, then I have my EY, then I have my EX. Okay, then I have the portions of the frame CBD, right, and this is my pulley right here. Okay, and this is the cable, right? If this is W, right, then we know that this is also W because it is a continuous cable. Okay, since it is a continuous, so this is also W, such that this is also W. Okay, so that when we try to put this cable back together with the upper free body diagrams and with this component right here, this W will cancel out each other, right? Okay, so but we are still missing CY, CX, and then we have here is BY, BX, and we can make a boundary right here, and we can call this upper free body diagram A, and then we can call this is upper free body diagrams B. Okay, okay, and from the upper free body diagram A, okay, we can, using the sum of the forces in the Y, we know that EY in here is equal to 0, right? So we already proved and show that EY is 0, and sum of forces in the X equal to 0. In here we show that EX plus W is equal to 0, so my EX is negative W, 735 newtons. Okay, so this quantities are not being asked, but it's good to show that to you that we are able to calculate that quantities as well. Okay, and then we go back to this upper free body diagram B, right? We go to this upper free body diagram B, and let's make okay, so by taking some of the moment at C, okay, I will be able to calculate BY. Okay, remember that because when I write sum of moment at C, CY and CX will have no contributions, similar with BX. The only force that has contribution is BY and W. Okay, so in here we have BY, okay, times 2 meter. 2 meter is the distance from here to here, right? Okay, and then from this W right here, the green one, I have W, right? And then the distance from here to here is 2.8 meter, right? It's given in the problems, and it has negative sign because this gives a clockwise rotation, right? And then is that all? Well, we still have this force right here, right? The W from the upper cable, right? From this cable on the top of the frame CBD right here. So we have to include that because there's a moment arm, right, with respect to point C. So that W times 0.3 meter, because the diameter of pulley in here is given in the problem is 0.3 meter. Okay, so and it has a counterclockwise rotation, so it has a positive sign. We set it equal to 0, so we will be able to calculate BY in here is equals to Newton. Okay, 919 Newton. Okay, right, so we solve for BY. Right now I will make a temporary jump to lower free body diagrams. Okay, because without making that, I will not be able to solve for bx and cx in here. Okay, if you write sum of forces in the x directions, it will not be able to solve for those two unknowns. Okay, so the easier way that I find out is that I have to go to my lower free body diagram first. Okay, and notice that the distance in here is 1.5 meter and distance right here is 2 meter. Okay, such that in here, if I take sum of the moment at A, okay, when I take sum of moment at A, I have by times 2 meter, okay, and it's a clockwise, so it has negative sign, plus bx times 1.5 meter equal to 0. Okay, and bx is positive because it's counterclockwise, is making counterclockwise rotation with respect to point A. Okay, so from these equations, I can calculate that my bx is actually equals to 1226 Newton. Okay, so after I obtain my bx in here, okay, I can go back to my upper free body diagrams, right? Right now, when I write my sum of forces in the x, okay, sum of forces in the x directions, I have cx plus bx, both are positive because they're going to the right, and then I have negative w, okay, and I use the red colors, which is to indicate I'm this one is the one that I'm looking at. Okay, and those are the forces in the x direction, and set it equal to 0. Okay, and in here you can see that before pre-calculating the bx from the lower free body diagrams, I cannot solve for this cx and bx from here, but once I already know what is bx, I can easily calculate my cx. In here is w minus bx, and I obtain is equals to negative 490.3 Newton. The negative sign means that cx has actually is going to the left, opposite to the initial direction that I'd assume in my upper free body diagrams. Okay, and then the next equations that I can write is sum of the forces in the y. Then I have cy plus by and minus w. I use the green color because this is the w that I'm looking at. Okay, so I already know by. I can calculate my cy is equal to w minus by, and in here I obtain negative 183.875 Newton. Okay, all right, and then that's pretty much everything that are being asked from these problems, which is to calculate what is the pin connection forces and reaction forces at C. Okay. However, I think there's one thing that we can do in the finalized part, which is to calculate the resultant of the reaction forces at C. In here we have by taking the square root of cx squared plus cy squared, right? And I will let you calculate this on your own because we already have the components. Okay, and then same thing, we can calculate the resultant of the pin forces at B by taking bx squared plus by squared. Okay, and I will let you calculate this on your own because we already have the component value in here. And later, when in the deformable bodies or strength of materials class, we are going to use this resultant force to design the diameter of the pin that we are going to use to connect the framing members in here. Okay, all right, I think that's pretty much that's it that I would like to say. And actually there are one more thing, I guess. If we're going to continue in here, if I take sum of the forces in the y equal to 0, right, I know that my ay is equal to by, right? That my ay is equal to by, and when I take sum of forces in the x, Okay, from the lower free body diagrams, I know that my AX is equal to BX. Okay, so what does it mean, right? What does it mean? So let's do another sketch right here. Okay, so just really quick. So we have join A, join B right here, right? So BX is 1226 and BY is 919. Okay, so the resultant force is going this way, right? The resultant force, right? And the resultant of force A is just going to the other way, right? And it has to be collinear, right? The resultant force A is just going to the other way right here. Okay, right? And you can see this is similar to the concept that we have learned in previous lectures related to the two force members, which state that if we have members that are pin connected at its both ends and there's no load applied within the span of that members, then the connector forces at the ends of the members has to be collinear. Okay, and you can see that right now the resultant of the connection forces at A and B in here is collinear, and they are going inward. Okay, I think that's enough to say for this lectures, and thank you for listening, and please let me know if you have any questions.